All right, good morning. So this is your supplement video pertaining to transition metals. So before we talked about binary and tertiary, and so this is going to be our conversation pertaining to transition metals. So first thing I want to do is highlight some of the transition metals that you're going to need to make sure that you know the charges for. And again, this was described and explained to you in the Ionics, but again, I wanted to go back through and touch base on these just so that way you have a good, clear understanding of what your expectations are. So now I'm just going to show you on the right hand side what those charges are for the different metals. Now, titanium is one of those that we will work with, but I want to just make sure you understand that titanium can have many oxidation states, but the two primary are +2 and the +4. Chromium is +3 and +6. That's what you'll see me use quite often, but there is a +2 oxidation state for it as well. And I do not expect you to know every single detail about these, but you do need to know the ones that I am writing for you right now. So let's see. So copper is +1, +2. Silver is +1. Gold is +1 and +3. And then zinc is +2. And then you get to the last two, lead and tin are both +2 and +4. Now there is a way that you can learn these to make things easier for you. A good way of doing that is sort of using the group numbers they're in, like 1B, 2B, and then you got 4A, which is ±4, which you can't have a negative charge for the metals. Not in our case. We will never see that. So these are always going to be +4s, and they also can be +2s. But again, this just comes with practice. The best thing to do is set yourself aside some flashcards and just make sure that you start to learn those. Now, what's the purpose of that? Now, remember that for transition metals, we use Roman numerals to establish what the oxidation state / charge is for the metal ion. And so again, any of these metals that are found in the transition metals are fair game, but the ones that you should know are the ones that are highlighted in yellow here. Those are the ones that you should know. Now, anytime you figure out the oxidation state, we must back calculate to determine it. All right, so we're gonna back calculate it using an element that is known. So most commonly, you're gonna come across things that are like this. All right, in which case you're going to have a somewhat of an understanding, because what you'll be able to do is you'll be able to pick out and establish that the anions themselves, you will know what their charges are. Now, we're going to start off with this TiO2 here, and I'll just kind of use it as a starting point. So what we do know is the charge of the oxygen. It's -2. You can look that up on the periodic table. It goes back up here. 1, 2, 3, 4, 3, 2, 1. So it's that pattern. As you go up, it's positive. As you go down, it's negative. So oxygen is a group 6A. So it's -2. Now, there's 2 oxygens, so that the overall negative charge is -4. Well, what cancels out -4? +4. So that means if we look at the formula, there's only one titanium, so that one titanium has a +4 charge. Now, in terms of naming that, we would write titanium (4) oxide. So, and I'm going to highlight this this here. I'm actually going to bold print it here. So you get this titanium 4 oxide, and that 4 is established from the oxidation state that we determined. Now that's the first one. So the second one was the Cr2O3. Now again, you do know the oxygen's charge, but what we don't know is the oxidation state for the chromium. So oxygen is -2. There are 3 of those, so 3 times -2 gives me -6, and then +6 will cancel that -6. Now, unlike what we saw in the titanium here, there was only one titanium, so that means that one titanium takes on the charge. But in this example, there are 2 chromiums, so you have to split the difference. So 6 divided by 2 gives me +3. And so the name for this would be chromium 3 oxide. And so again, this 3 is established from the oxidation state that you determined. So whatever's in that box that you're filling in is what you put in parentheses. And that's going to be the same pattern throughout everything that you do in terms of transition metals. Now this one, this is the other example that I wrote down. So now this one's a little different because we're not focusing on one element that you see from the periodic table. What we are doing is we're focusing on the fact that you have a polyatomic ion. Now that polyatomic ion has a -1 charge on it. There is only one of those polyatomic ions, so that means that the overall negative charge is -1, and the +1 is going to cancel that out. That means that the silver is 1 in its oxidation state. Now, earlier I gave you a list of these, all right, and silver has only one oxidation state of +1. So when you work with the silver compound, you do not have to worry about the Roman numeral. All you have to do is type the name silver nitrate in, write it out, whatever the case is. And so I want to make a short comment here that both silver and zinc have only one oxidation state, and so you don't have to write Roman numerals for those 2. And again, the reason for that being is that there's only one oxidation state, so zinc can only be +2, silver can only be +2. So if I were to take, let's say, zinc chloride, and I would write the formula for it, it would just be Zn. All right, we know Zn is +2 because that's the only thing, and then the chlorine is -1, so we would have a formula of ZnCl2. All right, so those 2 elements are a little bit easier in terms of not having to worry about the transition metal being using a Roman numeral. You don't have to stress about knowing what the charge is because you already know what its charge is. It's either +1 or +2. Now, if I were to come in here and say lead 4 sulfide, well, here is the name. But what I want to do is figure out what the formula is. So we have Pb. Its charge is +4 because it's got a Roman numeral 4. And then the sulfide itself is with a sulfur and a -2 charge. Now, we know that the charge of the lead is +4. So that means the charge of the sulfur has to be -4 to cancel out that +4. But the sulfur has a -2. So what we have to do is simple division here. So 4 divided by the 2 gives me a subscript of 2 for the sulfur. So that's using the Roman numeral and the basic charges that we've talked about earlier in figuring out the overall formula. All right. Now we could have wrote down Pb CO2 S4. We could have wrote it down like that, And then we could have simplified this to 1 and 2, but we didn't have to do that because, again, we know the charges. All we have to do is figure out what the charge is going to be to balance out, and then divide out, and that gives you the number. So sometimes it's a little bit easier than that. So let's say we have a copper 2 oxide. All right, so let's say we have copper 2. I'm going to use a different one. Let's do hydroxide for this example. All right. Actually, I'm going to change that. I'm going to do sulfate. All right, so let's do copper 2 sulfate. So copper has a +2 charge. And then the sulfate, if you look at your polyatomic, if you haven't memorized this, which you need to make sure you do memorize this, I told you that earlier, you will have a -2 charge. So the nice thing about this one is that the +2 and the -2 are going to cancel out, so you are left with a formula of CuSO4. All right, so again, the copper, the Roman numeral 2, tells you the charge of this. The sulfate with a -2 charge comes from memorizing those polyatomic ions. All right. So let's do a couple more here. So let's say we have WO4, and then let's do one more here. Let's do CrO2. All right. So let's start off with the tungsten. All right. So what we're going to do is name the compound. So this is going to be tungsten something oxide. So what we need to do is figure out what goes in the parentheses. All right. So we're going to go back and we're going to look at the fact that the oxygen has a -2 charge. 4 times -2 gives me -8. So what cancels out -8? +8. Now tungsten is one of those that you don't have to worry about memorizing. So that's why I wanted to do one with you so you could see how it would be done. So there's only one tungsten, and that means that that one tungsten must have an oxidation state of +8. So that means the Roman numeral that you would put in place here would be 8. So this would be tungsten 8 oxide. So that's what the name of that would be. Now, again, we've done one like this before, but we're going to do it again. So the chromium, we don't know exactly what its oxidation state is. Now, earlier we talked about the fact of chromium having a +3 and a +6. So it is possible that chromium could have something other than that. So, and it's not against the rules, but we're going to figure it out. So 2 times -2 gives me -4. All right, +4 cancels out that -4. That means that this chromium has a +4 oxidation state. And so naming it, we're going to use a Roman numeral of 4 to signify what the oxidation state is for that chromium. So the name would be chromium 4 oxide. All right, and so this is the basic pattern as you go about trying to figure out what those oxidation states are for the different transition metals. So one of the things you can do again is to learn and memorize these charges for these few elements here that I posed to you. But just know that it's possible that we can work with any of the transition metals in given certain information, just like we did with the tungsten and the chromium down here. We used the information for oxygen to back calculate what the Roman numeral should be for both tungsten and chromium. So again, if you guys have any questions, feel free to shoot me an email or whatever, and then I'll be glad to get back to you. Thanks for watching.